Hello, welcome to Dr. T's Math. In this video, we'll look at what happens when we've got a radical on the bottom, and that'll segue into asymptotes and wholes and parts of graphs, features of rational expressions. And so what we have here is an opportunity to simplify. Let's look at the top. We can take out a 3, obviously, 3 times x plus 1. And then on the bottom, let's look at the inner function here. So this is all going to be to the 1/2 power. Negative x, well, let's see. How about if we just took out a negative 1 first? Negative 1 times x squared plus x minus 20. Well, that's easily factorizable. The factors of 20, 4, 5, 10, 2, and that's it. So obviously if we had plus 5 minus 4, that would give us this 1 here. And so we're going to get negative 1 times x minus 4 times x plus 5. Okay, that got us somewhere. And all of that's raised to the 1/2 power. Well, can we solve for x? Sure. Well, if all this is equal to 0, then we just don't ever have to worry about denominators. Imagine all of this is equal to 0. Just put a star here, equals 0. So then denominators don't matter in the world of equals 0. And so what we would get is 3 times x plus 1 is equal to 0. X is equal to, again, those don't matter in the world of equals 0. So x is equal to negative 1 there. Well, is x equal to negative 1? Does that tell us anything? Let's have a quick look at a graph here, because we don't have an equal to sign. But if this were all y, imagine all of this were a function itself. So this is now y equals f of x, or y. Let's look at what the graph looks like. 3x plus 3 over root negative x squared minus x plus 20. So we've got 3x plus 3 divided by square root negative x squared plus x minus 20. Correct? Or sorry, that should be minus x. That's right. Real part and imaginary part. Well, it looks like from the bottom graph here, from the bottom one, we've got some asymptotes at roughly 3 and negative 3. And so let's have a quick look at that first. Asymptotes. So are there any numbers which we could substitute for x, which would give us 0 on the bottom? Anytime we've got a rational expression, which is a numerator containing letters and numbers with some operators, and then a denominator with some letters and numbers and some operators. It's a rational expression. Are there any numbers for which x would return 0 in the denominator? Well, yeah, I think we can see that when x is equal to 4, x minus 4 is going to be 0. Anything times 0 times 0 is going to be 0. And then when x is equal to negative 5, it's going to return a 0 there again. So that's going to be where we have our vertical asymptotes. Those are vertical asymptotes. That doesn't explain the behavior of the graph that we saw a moment ago. But vertical asymptotes exist when the denominator is equal to 0. An asymptote is, let's have a quick look over here. An asymptote is an imaginary line that the function is not going to fully reach. It might cross it in terms of like spring functions and things like that. Generally speaking, it's actually not going to touch it, but sometimes for spring functions it does. Let's have a look at that function again. So we're going to have y equals 3x plus 3 divided by square root negative x squared minus x plus 20. Okay, so we're showing vertical asymptotes here. What is going on over here? X squared. Do I have this correct? It looks correct. Well, that sure is weird. Ah, minus 20. That's fine. Sorry. It should be a plus 20. Well, so we went investigating asymptotes because of what looked like horizontal asymptotes, which only existed because of a mistake when I input the function. Here we are, the correct function, and indeed it has vertical asymptotes, nothing to do with 3 and negative 3, but in fact it's looking like what are asymptotes here. It's going to say it right there. X is all real numbers between negative 5 and 4. So it never actually gets to negative 5, it never actually gets to 4. It's all real numbers. It's continuous within there. Looking back at this graph, can we confirm? Yeah, it looks like it is extending only to negative 5 and 4 going upward. And so those were our two vertical asymptotes there. Do we have any horizontal asymptotes? Well, looking at the next slide, we see a different example up top. Well, let's look at the middle part here. Or to the bottom, actually. We have horizontal asymptotes. If the power, the highest exponent in the numerator is greater than the highest power in the denominator. Indeed it is. Here we have x to the first power up top, and on the bottom we have x to the 1/2 power. That internal function is our x there. And so there are no horizontal asymptotes on this graph. And we saw that just a moment ago, but there are two vertical asymptotes where the x value will make the denominator 0, forcing an undefined vertical line, which is not a function. If it were a vertical line, it would not be a function. So it'll get very, very close to a undefined or vertical slope, but never actually reach it. Continuing on, if the power of the numerator is less than the denominator, we've got a horizontal asymptote at y equals 0, and if it's equal, then it's the ratio of coefficients. Let's have a look at that top function on this page now. So we've got two functions, and this is a proper rational expression, where you got p of x over r of x, so we've got a quadratic over a binomial, and then r of x here, we're just looking at defining what the features are. In this case, ax plus c, a is 1 of those things we don't have to write because it's implied. And let's look on here. Well, obviously we have a vertical asymptote at x equals 4 because 4 minus 4 is 0. Anywhere that the denominator is 0, we have a vertical asymptote, and there's only that one. But let's look a little further. If p of negative c, that's on this here, so negative c is going to be 4, divided by a is 1, so 4 divided by 1 is 4, is equal to 0, then r of x, that's x minus 4 here, is a factor, and negative c over a is a root. Negative c over a, again, in this case, would be 4 over 1, or 4. So if we substitute 4 for every time we see x in that equation, and it returns 0 as an output, then that that denominator there is in fact a factor. Let's look on. We can decompose this. These statements are all made true by long division. Let's look up here. So we're going to go backwards and forwards a little bit, just like this little spring function, which does cross the asymptote. It's one of those few that crosses the asymptote. So we've got this quadratic up top and this binomial on the bottom, and we can test it using the factor theorem, which states that if 4, which is negative 4 divided by 1, if 4 as x returns 0 when we plug in 4, then this whole binomial here is a factor, and 4 would be a root, right? We could then do some long division. Let's do some long division before we go back into that slide. All right, so here, polynomial long division is going to make us take this value here, 6x, and divide into that x. How many times does x go into 6x? Well, it goes in there 6x times, and then we're going to get 6x times x is 6x squared. 6x times negative 4 is negative 24x. And just like regular long division, we'll subtract all of that. We get 0 here. And then negative 26 minus a negative 24 gives us negative 2x. Drop down that plus 12, just like regular old long division. Divide only that first term into this first term for negative 2. Multiply back that negative 2 by x, we get negative 2x. Negative 2 by negative 4 is plus 8. And then subtract all of that, subtract the negative, you get a positive, those cancel out. And then 12 minus 8 is 4. That then is our remainder. Since there is a remainder, we know that p of c, negative c over a will not equal 0. Right? We know that there's a remainder. Let's go back and calculate that. P of 4 is equal to 6 times 16, 4 squared, minus 26 times 4 is 20 times 4 is 80. We can do that next time. 26 times 4 plus 12. And so 6 times 16, 6 times 10 is 60, 6 times 6 is 36, that's 96 together. 20 times 4 is 80, 6 times 4 is 24. That's 104, but we're going to add a negative. It should be a negative. 96 minus 104 is negative 8. Negative 8 plus 12 is 4. So it's a quicker, easier way of finding the remainder, or finding out if it's a factor. And so now that we know there's a remainder of 4, well, that's where that number comes from. 6x minus 2 is this number here, looking back. 6x minus 2, so here's our 6x minus 2. That was our quotient. And then we've got plus the remainder divided by that first denominator there. And so then we could take this here, our quotient is q of x, and then we're plus a constant divided by the initial denominator here, c over r of x. And we could split that up into parts and we could multiply then this r of x by q of x. Q of x is 6x minus 2 here. R of x is x minus 4 there. These two FOILed out equals 6x squared plus or minus 26x plus 8, and then we add to that 4, we get our initial numerator there. And so, therefore, therefore, p of x, that's our initial numerator, is equal to q of x, that's our quotient, times the original denominator, r of x, plus some c, which is our remainder. Ta-da! And then a quicker, easier way of doing the long division also is synthetic division, where we're just going to take that negative c there, and it has to be where our value a is equal to 1 here. And in a later video, we'll look at when a doesn't equal 1, then you'll have to do that negative c over a there to get this value. But anyway, negative c is negative 4, positive 4. We're just going to drop down that 6. The 6 comes from our coefficients. We're just going to put together coefficient, constant. And if there were zeros, so you put the zeros too. So drop down the 6. We're going to multiply diagonally, add vertically. 4 times 6 is 24, add vertically. Negative 26 and 24 is negative 2. Multiply diagonally, add vertically. 4 times negative 2 is negative 8, add vertically. 12 minus 8 is 4. And there's our remainder again. And these are our coefficient and constant, 6x minus 2. So it's all related in the world of rational expressions, polynomial division, synthetic division, and then there's a little bit of vertical and horizontal asymptote mixed in, because if we had a slant asymptote, you're going to have to use long division or synthetic division in order to find the equation of that slant asymptote, which we'll get into in another future video. All right, thanks for watching Dr. T's Math. See you later.